In this lecture, we will discuss moving into processor performance as well as pipeline processor design. We will get started by focusing our attention on understanding appropriate considerations that need to be made in order to measure the performance of a processor. And this is an important aspect of architecting and constructing a processor because the architectural features need to be based on expected performance. And so what we'll do is focus our attention on understanding appropriate ways in which we can quantify processor performance. And so we can consider using appropriate metrics initially. And so you want to keep in mind that if we're going to try to make processors better, incrementally improve the performance, then we need appropriate attributes that can be utilized in order to quantify that performance. And so some common metrics that come into play when we're trying to evaluate processor performance include making sure that we have an understanding of the space complexity, and this relates to the memory footprint that application or instruction set encompasses. We also need to be sure that we're aware of the time complexity, and this relates to the execution time of the application or instruction set or data path that we're analyzing. We'll also need to make sure that we're aware of the instruction frequency as it relates to how instructions within the application are executed. And when we talk about instruction frequency, we talk about it in terms of static frequency of an instruction as well as dynamic frequency of an instruction. And so we'll further discuss these attributes as well. And then we also need to consider appropriate benchmarks that would be utilized in order to measure processor performance. So what exactly determines execution time of a processor? And so in order to understand that, we need to understand the attributes that constitute the performance of a program on a processor. And so when we think about the execution time, we're considering the sum of the clocks per instruction times the clock cycle time, where J is greater than or equal to 1 and less than or equal to n. So we sum up all of the instructions that would be executing and multiply it by the clock cycle time. So this is essentially, we're going to compute a large number of instructions. And so in order to do this at a larger scale, let's say we consider billions of instructions, we take the execution time to be n times the CPI average times the clock cycle time. And in this case, we want to denote that n is going to be the number of instructions that are executed. And so it's important to keep in mind as we identify and define static versus dynamic instructions that n is going to represent the dynamic instructions that are being executed. And so let's start with the example. If we have let's say we have a 1 gigahertz processor that is executing 10,000 instructions with the CPI average of 3. So if we were to compute this, we would need to consider the speed of the processor. And we're going to multiply that by the number of instructions that we have. And then we're going to multiply that by our CPI. And so as we work to reduce that, it will simplify us to our result. And so that's a simple enough approach for executing, for determining the execution time based off of given parameters such as the processor speed, the number of instructions to be considered, and a known CPI. And so now we can talk about components that affect instructions, and that is going to be broken down into the instruction frequency. And we think of instruction frequency in two terms, and that's going to be static instruction frequency and dynamic instruction frequency. So let's consider static instruction frequency. It's going to relate to the number of times a particular instruction occurs in compiled code. So static instruction frequency can affect various aspects of our performance, and it has an impact on the memory footprint of your instruction group or data path. And it also has important to consider that if a particular instruction appears a lot in a program, then then we need to occupy the space in an effective manner. We also have dynamic instruction frequency. And the dynamic instruction frequency refers to a number of times a particular instruction is executed when the program is run. So this can impact the execution time of the program. And if the dynamic frequency of an instruction is high, then we want to make appropriate enhancements to the data path to help control and ensure that the CPI taken for execution is minimized. So in this sense, we get an understanding that dynamic instruction frequency has a great effect on the performance and execution time of an application or data path that we're going to be considering or focusing our attention on. So again, just a little sanity check. When we think about static instruction frequency, what are we referring to? Are we referring to the type of instruction in the instruction set? Are we referring to the frequency of occurrence of instructions in compile code? Or are we referring to the frequency of occurrence of instructions that actually get executed? Are we referring to the clock frequency of the processor? Or are we considering it to be the basis for our data path design? So you want to recall that we're referring to the number of times or the frequency of occurrence of an instruction in our compile code. So let's consider a little sanity check for considering dynamic instruction frequency. When we refer to dynamic instruction frequency, are we referring to the type of instruction in the instruction set? Are we referring to the frequency of occurrence of instructions in compile code? Or are we referring to the frequency of occurrence of instructions that actually get executed? Or are we referring to the clock frequency of the processor? Or is dynamic instruction frequency the basis for data path design? And so in this case, we want to be sure that we remember that the dynamic instruction frequency refers to the frequency of occurrence of instructions that actually get executed. And so let's consider a problem where we need to determine the static frequency. Let's say we have an add instruction that occurs twice in a program that contains a total of 1,000 instructions in the compile code. All 1,000 instructions get executed during a program run. One of the add instructions is in a 5-instruction loop that gets executed 1,000 times. And so what is the frequency of the add instruction in considering? Is it 2? Is it 0.2% frequency? Do we consider 1,000 divided by 5,995 times 100%? Do we consider 1,001 divided by 5,995 times 100%? Do we consider 1 divided by 5,000 times 100%? Or do we consider 1,001 divided by 5,000 times 100%? And so some things that we want to keep in mind is that we're going to need to keep in mind what is the memory footprint of the program. And that memory footprint that we're given is 1,000 instructions. And so how many adds do we have? We're told that we have an add instruction that occurs twice in the program. And so in order for us to compute the static frequency of the add instruction, we'll take 2 divided by 1,000 and multiply that resultant times 100. And that will give us B, which is 0.2%. So essentially everything that we need to know to solve this static frequency problem is what is given to us in the first line of the question. We have the add instruction occurs twice in the program, and that contains a total of 1,000 instructions in the compile code. So we say 2 divided by 1,000 times 100 gives us 0.2%. Now let's consider what is the dynamic frequency of an add instruction. So we have our problem and it says the add instruction occurs twice in a program that contains a total of 1,000 instructions in the compile code. We know all 1,000 instructions get executed during a program run. One of the add instructions is in a 5-instruction loop that gets executed 1,000 times. Okay, so now we have a different question in that we want to know the dynamic frequency of the add instruction. And you need to be sure that you remember the differences between the dynamic frequency versus the static frequency. And we want to remember that the dynamic instruction frequency is going to refer to the frequency of occurrence of instructions that actually get executed. And so let's consider how many add instructions are executed during the program run. We know that we have 2 instructions in the program, but how many times are they executed? So let's consider that 1 instruction is in a 5-instruction loop that gets executed 1,000 times. So how many times is the add instruction being executed? It just says 1 add, so that means it's going to execute 1,000 times in that loop. It says it's a 5-instruction loop, but we don't worry about the other 4 instructions that are present. So we'll have 1,000 plus 1, which means we have 1,001 total ads that are executed. So now let's consider the total instructions that are executed. We have 1,000 instructions minus 5 plus 1,000 times 5. So we're going to have a total of 5,995 instructions. So to calculate the dynamic frequency, we're going to say 1,001 divided by 5,995 times 100% to get our dynamic frequency. So this has allowed for us to have an understanding of how to utilize some initial metrics for execution time and calculating the frequency of the static and dynamic frequency of instructions. So now let's talk a little bit about or introduce benchmarks. And what exactly are benchmarks? Well, benchmarks are a set of programs that are representative of the workload for a processor. And so essentially a benchmark can be utilized as a point of comparison and comparing different features of a processor, or not just a processor or of a system. There are benchmarks for calculating the interconnect speed in systems, for calculating bus speed, for calculating memory speed, as well as for the processor as well. And so the key difficulty is to be sure that the benchmark that you're using is representative of the prospective workload. And that can be a difficult task to understand because one benchmark might be very heavy computationally, but then another benchmark might be very heavy memory-wise. And so you have to determine what benchmark is going to represent the type of application that you're dealing with. If you have a big data application that is very memory intensive and data intensive, but less so compute intensive, then a compute intensive benchmark is not going to be a good benchmark for you to use to help identify the type of system or platform that you want to use. And so there are a number of standard benchmark suites that are used in order to try to compare performance. And so these are normally utilized a lot in scientific computing and measuring the performance of specific applications. We have Spec Benchmark, LinPack, Whetstone, Drystone, and there are many others as well. The NAS parallel benchmarks can be utilized, and a lot of times the benchmarks are going to represent high-level mathematical computations that can be used in order to determine the validity of system performance for a respective application. And so in many cases, system architects will try to use benchmarks to help guide them in processor design and construction. But if things are too off base, then a design that is just too radical or too different from available designs a benchmark might not be able to provide the insight that is needed. And so there are a number of different components that can be considered when evaluating processor performance with a benchmark. And so there are a number of different performance indicators that can be used. And so We've talked about the total execution time. This is going to be the metric that's a cumulative total of the execution times of individual programs. We've talked about arithmetic mean. This is going to be a metric that may bias the summary value towards the time-consuming benchmark program. Geometric mean is going to be a metric that tries to remove the bias present in an arithmetic mean. We can use a weighted arithmetic mean, and the weighted arithmetic mean is going to take into account the relative frequency of the execution of programs in a benchmark mix. And so essentially that's going to represent a weighted average of the execution time for all of the individual programs being executed. And then you also have a harmonic mean, which is going to be another composite metric, and it's going to be calculated by computing the arithmetic mean of appropriate reciprocals. And so this can help any bias towards high values that might be present in the arithmetic mean. And so with the arithmetic mean, it's important to keep in mind that this might result in a high bias. Geometric mean is more considered towards in the middle. So you won't have a bias too high or a bias that is too low with the geometric mean. And so some things that you need to consider based on using a benchmark. That the biases of composite functions, we have to be very cautious using a single composite metric in analyzing the performance from a benchmark. Also, there are various factors that can affect processor performance. It's not going to necessarily just be determined by the speed of the processor or the clock cycle rating. Memory organization and memory utilization of the processor, as well as the bus bandwidth and latency, are also key components that can affect benchmark performance. And of course, some processors are going to do well on certain benchmark programs and others might not. And that can be inherently based on the goals of the benchmark, might be more aligned with a specific processor construction versus another. You want to keep in mind that a composite index can be useful when we want to compare two processors without knowing the exact kind of workload they're going to run. But we need to also be cautious about the overuse of metrics. And of course, the old cliche, lies, damn lies in statistics. And so, of course, there are also various reasons to be skeptical about benchmarks. And so it can be a conflict if the vendor is giving you the benchmark results versus allowing a third party to test test their benchmarks on their system. So if the vendor wrote the benchmark suite, then of course they're going to try to make it appear as it provides the best performance for a given scenario. And so that's one thing to consider. Sometimes the benchmark suite doesn't seem to have the appropriate elements that are needed to represent workload. And so this can be that, if you run your web server and the benchmark represents only computationally intensive scientific calculations, then it might not be appropriate. Also, other considerations, the equipment being benchmarked is different from the equipment you want to evaluate. The benchmark uses a different compiler suite than you plan to use. And so the cost of mistakenly choosing the wrong equipment is very high if the benchmark is not an accurate representation. So these are some considerations that have to be kept in mind when using benchmarks. And it's important to keep in mind that all major developers and vendors, from IBM to Intel to Apple to NVIDIA, they make use of benchmarks in order to test the performance of newly architected chips and systems and to provide a standard of measurements against their current systems. So benchmarks can be used to extrapolate and expand performance to help identify possible areas of improvements that might be needed within a system design or architecture design. So let's consider in creating a composite performance metric using an arithmetic mean. What will happen? Will this reduce bias included in the geometric mean? May bias the summary towards time-consuming programs in the benchmark? Yields a cumulative total of the execution times of the individual programs? Or does it takes into account the relative frequency of the execution of the programs in the benchmark? And so if you remember, arithmetic mean is going to be a cumulative sum. And so this could result in the bias, the summary towards time-consuming programs in the benchmark. So let's take a look at kind of an overview or summary of what we have covered thus far. We've talked about memory footprint, in it that we want to be sure to represent the total space occupied by the program in memory. We talked about the execution time, where we consider the running time of the program as it executes in instructions. We've talked about the average of execution times of the appropriate components, the arithmetic mean. And so this is going to average constituent benchmark programs. We have the weighted arithmetic mean, where we're weighting the average execution times of the benchmark programs. And then we have the geometric mean, which will provide for a root of the product of execution times. And then we've also discussed static frequency, which relates to the occurrence of instructions and compile code, as well as dynamic instruction frequency, which relates to the occurrence of instructions in the executed code. So static will represent the number of times the instructions is present, and dynamic is representing the actual number of times that the instruction is executed. We have a few more metrics that we're going to cover in our next lesson, and these relate to speed up in terms of performance of speed up over machine A over machine B, speed up improvement, making improvements to a data path or instruction set, um, speed up in execution time, as well as speed up, as well as measuring performance improvement using Amdahl's law. So that is the next set of metrics and concepts that we will cover in the next lesson.